Welcome. Today we shall be doing a few more problems on the refrigeration and liquefaction. So in this lecture we shall be looking at the Linde dual pressure liquefaction system and Claude liquefaction system. So let us take the first problem. Here we are given a Linde dual pressure system that is operating with nitrogen as the working fluid, and the lower pressure is about 101.3 kilopascal, that is about 1 atmosphere, and 300 K. It means that we are taking this nitrogen at the ambient condition, and this particular gas is being now pressurized to about 20.3 megapascal, that means at around 203 bar. The intermediate pressure is 5.07 megapascal and the intermediate pressure flow rate is about 0.80. So this has been given that this flow ratio has been given as 0.8 and this is given as the intermediate pressure. And what we determine? We determine the liquid yield, the work requirement per unit mass of the gas compressed, and the work requirement per unit mass of the gas liquefied. Now you see here that here we are using a dual pressure system, and as we learned earlier that the dual pressure system reduces the work requirement per unit mass of the gas liquefied, and it also increases the decreases the yield a bit. So we shall be seeing that what kind of changes it brings about by doing this two-stage pressure. Now before we go on to solving the problems, let us look at some points, and these points should be remembered whenever you are going to solve any of the problems stated earlier, and also we are going to deal with later regarding the use of the various thermodynamic property data from the various sources. So first thing is this, we should always refer to, as far as possible, the same source of data for thermodynamic properties like entropy, enthalpy and internal energy. Why I'm talking about only these three properties? Because these three properties are quite often used, first, and second reason is this: all these three properties are given in terms of some reference values, and this reference value is again specified at some particular standard conditions. So there is nothing like absolute enthalpy, absolute entropy, absolute internal energy. All these three quantities are relative, and when you take the datum value as some specific value, or sometimes the datum value is also taken as 0. So in that case we say that with respect to that datum value, these values are having some whatever value are specified are the kind of absolute values. Okay, so if the datum changes, naturally these values will also change. So that way, this is the reason that one should be very careful and try to stick to only one source of data, so that there is no inconsistency in the final result. Otherwise, what happens that you may land up with some very absurd and non-physical result. And in case you find that it is not possible for you to get all the data from the same data source, then you may have to look for different data sources. As far as possible, make sure that all the data sources have the same standard conditions for the SHU. And if you find that this condition is not being fulfilled about the same standard conditions, then you have to resort to some equations which are given in the standard thermodynamics book to convert one data source datum to another datum. By there are some relations are there by which you can make the things at par. Okay, so these points need to be always kept in mind whenever you are going for any of the thermodynamic analysis. And in these problems or earlier problems also, we have been using the values of the entropy and enthalpy to calculate the work and the yield, etc. And we are taking the data from those two books which we are given in the reference, but there are many more data sources available. There you will find the values which we are specifying here in these problems may differ, so there you should be careful about taking those values. Okay, let us now get back to the problem. So here, to recapitulate, this is a dual pressure system. Here first we are doing that we are using two compressors. The first compressor is taking from the initial pressure, and in our case it has been given about 1 bar, and it is going to intermediate pressure, and that value has been given as near 5 megapascal, that is about 50 bar, and then we have been given the final pressure also. So these we are given the P1, P2 and P3, and then you found that we have using some kind of 3-channel, and here we are using 2 reservoirs. The first reservoir is simply sending the cold vapor back, and the second reservoir is from where we are getting the liquid. So this particular thing we have to keep in mind, and this is also we showed earlier. That's how this whole process can be represented on a TS diagram, and this is an ideal diagram where we are neglecting all kinds of heat losses and all kinds of enthalpy and the changes in the kinetic and the potential energies, and heat physics are neglected, and based on all this we generated this particular curve, which I am not going to discuss now. But what you shall see that here as per the given problem data, we are getting this value of the enthalpies and entropies from some thermodynamic chart, and which are given in the reference books. From that we are getting these values, and let us see that if you see that this H1 S1 conditions is with respect to these 2 points. Okay, so this is the inlet condition to the first compressor, and that is the state 1. So and at the state 1 we are getting the values of the enthalpy and the entropy, and we have also written the temperature. This is given as 300 K and 101.3 kilopascal. Okay, and now we go to the second data point which we need, that is the point 2. Now here you see this point 2 here in this TS diagram, and it is also shown over here, point 2, and this is also point 2. Why? Because this particular stream which is coming up, that is mixing up with this particular stream which is coming to the compressor. So these are states of these 2 streams ideally should be the same. So that is why this is also state 2 and this also state 2. So and this is state 2 here. So we are getting the values of the enthalpy and the entropy, and here you will see that the intermediate pressure is about 5 megapascal. Next we go to the third state, that is here after the second compressor. Here we find the after second compressor there is the highest pressure attained in the system. So at this point again we are getting the values of the H and S, and lastly we have last point, that is HF, that is at this point, that is in the second liquid this reservoir is there. So in this that we are finding that we are doing this isenthalpic expansion, and we are getting the saturated liquid. This liquid is being taken out from this position. Okay, so at this point is the HF, and please remember that we are assuming that this liquid is saturated and it is not subcooled. Okay, so that is why it is falling right on this saturated liquid curve. So this is the value we read from the TS diagram. Now let us go to the solution. So we put all these things here. This I represents the ratio of the intermediate stream to the total mass flow rate. This is given as 0.8, and we write all the values of the enthalpies and entropies, and also in this particular table. And now we found that in the Linde-Hampson dual pressure Linde-Hampson, this is the particular expression which we derived for the liquid yield. And as I said that this first one corresponds to the simple Linde-Hampson, and the second one is the one that is the contribution from the dual pressure system. Okay, and now we plug in the values of the enthalpies over here and the value of the I over here, and we get this as the liquid yield. Okay, so you can clearly see that if we do not take into account the second term, okay, then the liquid yield is more than this value. So there is a slight decrease in the liquid yield from 0.069, that is about 0.07, to about 0.205. So there is a slight decrease in the liquid yield. On the other hand, let us see that the work of compression, that here again we write the work of compression. We derived the expression earlier, and here you see this first term is representing the work done for the simple Linde-Hampson, and the second term is the contribution, and which is of with a negative sign it's coming. That means the second term is the due to dual pressure we are reducing the total work done, and this work done is found in terms of the total mass that is being processed. And again we plug in the values of the various quantities we wrote in this table or here, and we find this is the work done, which is coming to about 196 joule per gram. So you have to be very careful in using this particular values. See, all these values have been reported in terms of joule per gram. So this is joule per gram or kilojoule per kilogram. And now lastly we find what the work required per for liquefaction of unit mass of gas. So in this case we shall be using this is the modification over here. This will be divided by y. This will be mf. Okay. So this is mf. So this is we are getting from this. This will be mf. Okay. And this mf is mf. You know that mf by total m is this one you have to use, that mf by m is equal to y. Okay. So now you can see that from this relationship you can see that how this particular thing we can get the amount of liquefaction per unit mass of the gas liquefied. Okay. Now we go to the this particular curve you see here. This curve shows what? It shows that on the x-axis we are plotting the intermediate pressure, and on this y-axis, on this we are plotting the amount that is liquefied, and on this y-axis we are plotting the amount that is the work per unit amount the mass compressed. Now here this particular graph is showing that how with the change in the intermediate pressure and with the change in the flow ratio of the intermediate mass flow ratio, how will the liquid yield get affected and the work also get affected. Now you can see here that suppose I choose any value of the intermediate flow ratio and some particular curve for I. Now if I is constant, then you can see that as I increase the intermediate pressure, what I am finding that initially the work is decreasing. Okay, work done per unit mass of the gas liquefied, that is initially decreasing, and after certain value we find it passes to a minimum, and then if we further increase the intermediate pressure we find again there is an increase in the work done. Okay, that means this intermediate pressure is very crucial factor. It has to be chosen very carefully to minimize the work requirement. And on the other hand, we see that this particular for a given, suppose I take the given intermediate pressure is constant, and now I see that we change in the I, that the I is decreasing from bottom to top, and what we find that as we go to bottom to top, again we find that work done is increasing. So this kind of curves we can generate for any problem, and in the given problem what we have just seen, that in that you can change the values of the I, keeping the intermediate pressure constant or vice versa, and you can figure out the effect of these two parameters on the overall performance of the system in terms of the amount liquefied and in terms of the work requirement. More of these things will come to you in the assignments. Now we go to the second problem. In this problem what we find that we have a Claude system now, and Claude system, if you recall, this is based on an expansion engine. Okay, so this Claude system is liquefying nitrogen, and it is operating between this particular pressure and temperature, and this is a higher pressure which is the compressor doing. Okay, so here we find that this is about 1 atmosphere and this is about 50 atmosphere, okay, or 50 bar. The expander fluid ratio is 0.6, and the expander work is utilized to aid in the compression of the gas, and this is very important. That means the work which is obtained from the expander is also being used in the compressor. That means what? That effectively we are able to reduce the external work requirement to run the compressor. Now, if we are not doing this, that means we are not utilizing the turbine work or the expansion engine work to drive the compressor, then we find the compressor work will remain same as in case of the simple Linde-Hampson. The condition of the gas at the unit of expander is 270 K and this, and so we have to determine the liquid yield total work per unit mass of gas compressed and the work to liquefy a unit mass of gas. Okay, now let us do all these things. So again, we recall our this is a Claude system that we find we have 3 heat exchangers, and after this is being compressed isothermally ideally, and it is going to the first heat exchanger from where we are taking a stream out, and this is being passed through the expander. It is getting cooled, and this is coming to the return stream, and here we take the rest of the stream is taken for the liquefaction, and from here we are getting the or withdrawing the liquefied mass. And again we go back to the TS diagram representation. So here it is that from intermediate point is 3, that is 3 is here, we are withdrawing this gas, a part of it to the turbine. So and this is ideally undergoing an isentropic expansion. So here find that it is going to isentropic expansion, a straight line, and rest of the things is it is getting cooled by these heat exchangers, and ultimately at this is the valve, JT valve, it is undergoing the isenthalpic expansion, and we are getting the liquid over here. This is the liquid we are getting here, and from this is being withdrawn, and rest of the vapor, this is the vapor stream G, which is again getting heated up isobarically. From here to here it is going heated up, and it is ultimately reaching the same condition as the initial condition as at the compressor suction. Okay, so this is how, and here as we said that we are neglecting all the pressure drops through the pipeline, and we are also neglecting the heat and mass leakages in the pipeline. Okay, and now let us see that these are the values as earlier problem. We get the values of various enthalpies and entropies, and again we demarcate those points that this is the point on this curve and on this, and this is the point on the TS diagram. This H1 S1 is there, and then we go for H2 S2. This is point 2 is here, and here is point 2, and then we go to point 3. This point 3 is over here. This is the point 3 over here, and we read the value of H3, and then this is the value of the S3 and now S3, and because ideally this is an isentropic expansion, so naturally the entropy at the entry and the exit of the expansion engine will be the same. So that is why we are writing S3 is equal to AC, and these are found at this given temperature and pressure. Then we come to the HE value. At this point HE value, here we have the HE value over here, and that is how we get all the values at the various points which are required to calculate the work and the liquid yield. Now lastly we have this HF value. HF, we can see that this is at the 77 K, this is corresponding to the saturated liquid. Now coming to solution, again we write the expression for the liquid yield, and here in this case we find by using this expansion engine we are able to increase the liquid yield over what we get the simple Linde-Hampson. This is simple Linde-Hampson yield, and this is the contribution of the Claude expansion. Okay, and this Claude, so now ultimately we get this is the rise in the liquid yield, and you can see that in the simple Linde-Hampson you would get 0.02, whereas in case of this Claude system we are getting 0.27. So there is a substantial rise in the liquid yield. On the other hand, if you look at the work of compression, we see that because we are using the work from the expander, so it is reducing the overall work requirement by the compressor. And if we do not do this, if you do not use this work, then we will find this work is same as that for the simple Linde-Hampson. Again, plugging the values, we find that this is the work done per unit mass of the gas being processed. And for this mass of this gas, which is for per unit mass of a gas liquefied, again it is a MF, and MF Y equal to MF by M. Okay, so we are using this relationship and to find out the value of the mass work requirement per unit mass of the gas liquefied. Okay. So, this is how we do this particular problem, and now we see that again we are putting another curve like this, and here what we see that we are having the various pressures over here, and this is the various x values, expander flow ratio, and these are the intermediate pressure to which is getting expanded and the liquid yield. And again we find this sort of curves can be obtained to find out the effect of the expander flow ratio on the work done, and this is for air. So, this kind of things can also be generated for different types of working gases. And these are the two books, and these two books may be referred to for the detail about the processes and their calculation methods, and also to obtain all the thermodynamic properties which we have taken from these two sources. Thank you.